This Mathcast will walk you through section 11.2, where your students will apply calculus to parametric curves and vectors. Section 11.2 and Section 11.4 explore ways to apply calculus to parametric curves and vectors. This section, 11.2, will be fast-paced and cover a large amount of new information that in Section 11.4 will be pulled together in a fun application problem involving a robot battle. Section 11.2 will investigate ways to apply calculus to functions that are written in component form, such as parametrics and vectors. Now, since in many ways the same processes will be used on both vectors and parametrics, our first lesson in this section, lesson 11.2.1, will start by making sure that students still understand that there is a distinction between a position vector and a parametric equation that happens to represent position. Now, as you circulate, check in with each study team about how they answered Part C of Problem 11-40, which asks, what information does a parametric function give that a vector does not? After completing this problem, your team should be able to explain to you that initial position can be found by evaluating the parametric equation at the parameter t equals 0. But if they were to evaluate a position vector at t equals 0, that will not necessarily reveal the initial position. In fact, it doesn't really reveal any physically meaningful information at all. Problem 11-41 explores a parametric equation that describes the position of a roller coaster as a function of time. Your students will sketch the path of that roller coaster on their calculators, and then in parts A through C, they will differentiate to determine the corresponding velocity function for each component. They will then use those components to answer questions about the position and velocity of the coaster at various times. Now, it is stunning that the techniques that they will use to answer parts A through C are identical to what they would do if they were asked the same questions about a position function that was given rectilinearly. They just need to attend, in this case, to which components to use in each situation, but overall, it's the same strategies. So be sure to discuss this connection with your teams as you circulate. This discussion will make Part D seem even more powerful because Part D asks teams to compute speed. Now, if they were given a rectilinear function, they would merely need to take the absolute value of the velocity function. But when given a parametric equation, it's so much more complicated. So be sure to check in with each team to discuss the magnitude, no pun intended, of this part of the problem. Problem 11-42 explores the slope of curves, that is, dy over dx, which, if you're given a parametric equation, can be found by simplifying the ratio between dy over dt and dx over dt. Now, Part B of this problem is very important to discuss with teams as you circulate, or even to use as a prompt for a whole class summary at the end of class. This question asks, in the context of this problem, where y and x represent vertical and horizontal positions as a function of time, does the slope dy over dx represent velocity? Or if not, what does it represent? Now, many students might mindlessly answer yes, because they are so accustomed to slopes of tangent lines representing velocity when you're given a position graph. Now, of course, this would be true if we were given a rectilinear function, but it's not as simple on a parametric equation. So prepare some pocket questions to discuss this problem as you circulate. You might ask teams, well, what is velocity really? To which students will probably say something like displacement over time, or delta y over delta t, or maybe even delta x over delta t. But if they answer delta y over delta x or dy over dx, you're going to need to follow through with more inspection. So in that case, you might want to ask teams to describe an expression for the slope of a tangent line. They would say then dy over dx, or maybe vertical displacement over horizontal displacement. Now, this certainly does not represent velocity. So be sure to check in with every team about how they answered Part B, because not only will this conversation bring to the surface why slope represents velocity only when the horizontal axis represents time and the vertical axis represents position, but it will also bring to the surface a conversation about the meaning of terms that your students have been using for the whole year now, such as velocity, slope, and derivatives. Next, now that your students understand how dy over dx, or the slope of tangent lines, can be found by simplifying the ratio of dy over dt over dx over dt, the next problem, problem 11-43, introduces a situation in which that method will not work. Namely, when dy over dt over dx over dt yield a 0 over 0 or indeterminate solution. In this case, the parametric equation will need to be converted into a rectilinear form. Now, there are multiple ways to do this, but the most convenient would probably be to write that rectilinear form implicitly and then differentiate it implicitly and evaluate when t equals 0, noting, of course, that the parameter has already been eliminated, so your students will have to solve for the corresponding values of x and y before evaluating. Now, as I said before, there are multiple ways that students might reach this solution. So if you notice that there are a variety of compelling strategies being used in your classroom, use a study team strategy like a swap meet, where 2 members of each team circulate clockwise around the room towards their neighboring table, where they will share strategies that they used and also learn strategies that their neighbor used, and then rotate back to their own table where they will share and learn what was just communicated. Then this math note appears at the end of lesson 11.2.1. It summarizes the relationship between position, velocity, and acceleration vectors, and also how to calculate speed when given a function written in component form. And problem 11-53, which is the first problem in lesson 11.2.2, summarizes the concepts that were covered the day before. So allows students to reference their work from the day before as they complete these problems. Now, in order to keep this set of review problems very discourse-rich, use a study team strategy like pair to pair of teams, where students first work on part A through E with a partner. This would be sort of like a rough draft of the solutions. Then the partners refine their work by cross-referencing with the other pair of partners at their table in their team, discussing any differences. And finally, the final revisions happen by pairing up 2 different teams, again, to discuss any differences that they had until all 8 members of the 2 teams agree on the best solution path for each of these problems. Now that the work from the previous day has been reviewed, the rest of lesson 11.2.2 will explore second derivatives. Many common misconceptions are addressed in problem 11-54. So this is a problem that you will probably want to bookmark and refer students back to in the future if you notice that your students start making any of these common errors. For example, when given a position function that is written parametrically with time as the parameter, it is common for students to try to find concavity of the curve by incorrectly writing the second derivative. They write it as the ratio between the second derivative of y with respect to t and the second derivative of x with respect to t. But part B of this problem will force your teams to look critically at this common error and explain why it is wrong. And some guidance is given, namely, teams are asked to focus on the distinction between d squared y over d squared x versus d squared y over dx squared. This will provide you an opportunity to remediate what a second derivative really is. That is, second derivatives are the derivative of first derivatives, and what that means in terms of the arithmetic notation for second derivatives, and why, consequently, the ratio between the second derivative of y with respect to t and the second derivative of x with respect to t is not the same thing as the second derivative that determines concavity. Now, if a few teams struggle to make sense of this distinction, try not to do the thinking for them. Perhaps you could refer them back to problem 10-43 for a clue. That's the problem where your students remove the parameter in order to find first derivatives rectilinearly. Or you can use the I Spy study team strategy, where you allow a struggling team to send a spy around the room, observing what other teams are doing, with the task of bringing back ideas to their group. Of course, the spy is expected to do this discreetly and not engage in conversation with other teams. Problem 11-55 is a clever problem. It feels sort of like a puzzle because the given information includes an initial position, the horizontal component of the velocity function, not the vertical component, and the equation of the slopes of the tangent lines, which stealthy students will recognize to be dy over dx and then use that relationship to determine the vertical component of velocity and work from there. Now, because the given information is so puzzle-like and non-traditional, this would be a good problem to use a teammates consult study team strategy, where before putting any work on their papers, your students first prepare silently and individually, and then through a team discussion, and then they'll start working. So for this one, give everyone some think time, and then allow the teams to discuss their strategy, and finally allow them to pick up their pencils and execute. And Lesson 11.2.2 concludes with a math note that summarizes the tools that can be used to compute the slope and the concavity of a parametric curve. The last lesson in section 11.2, lesson 11.2.3, will explore how to find the arc length of a curve whose equation is given parametrically. Recall that the arc length formula for rectilinear curves was introduced back in section 8.4. Now, the first problem of this lesson, problem 11-62, foreshadows a very big upcoming problem at the end of this chapter. That problem will be called the robot battle. And in this problem, one of the robots, Mach 1, is being programmed with a parametric equation that tells us its velocity, and we're also given information about its starting position. So in part A, your students will use that information to write a parametric equation that represents position of Mach 1 on the coordinate plane starting at time equals 0. And then they will plot that parametric equation on their calculators and they will animate it. Now, information about how to animate a parametric equation on a TI calculator is provided in the teacher notes. And there's also information in the ebook, in the teacher notes for the ebook, about how students can create an online simulation on Desmos. It's the one we're looking at here. And a link to an example screen is provided in those teacher notes. Now, finally, your students will sketch the graph of the resultant parametric equation. And in part C, they will use that graph to estimate the total distance that Mach 1 traveled. Now, in order to help your students come up with a reasonable estimate based on the graph, it's a good idea to advise them to scale each axis by the same value. And in order to communicate this suggestion without stopping teamwork, consider using a huddle where only one member of each team comes up to you for a hint while everyone continues to work, and then they go back and communicate your hint to the rest of their teammates. Now, be ready. While making these estimations, many teams will just eyeball it, which they're supposed to do. But some teams might go a little beyond the intended scope of this problem and go and calculate the actual arc length or total distance traveled by converting the parametric equation into rectilinear form and then using the arc length formula that they know and have known since chapter 8. Now, while this is a valid strategy, we don't want it to take so long. So do intervene if teams are taking a long time because they're only supposed to estimate. And the rest of this lesson will explore ways to write a new formula that can be used to calculate the exact arc length of a parametric curve without rewriting it rectilinearly. So in problem 11-63, your students will transition between the arc length formula in rectilinear form to the arc length formula in parametric form. To do so, this problem will first explore how, unlike in rectilinear form, in parametric form, arc length and total distance traveled are equivalent so long as the object does not trace back onto itself. And also, just like in rectilinear form, total distance can be found by integrating speed. So In this problem, teams will have the opportunity to compare how rectilinearly integrating speed is the same thing as integrating the absolute value of velocity, but parametrically it looks different. In this case, the integrand, which represents speed, is represented by applying the distance formula to the velocity components. Be sure to discuss this distinction with teams as you circulate. The remaining problems in lesson 11.2.3 will allow teams to find arc length and or distance traveled along a parametric curve in a variety of applied situations. And the lesson concludes with a math note summarizing the connection between arc length, the integral of speed, and total distance traveled. This concludes our walkthrough of section 11.2, where your students applied calculus to parametric equations and to vectors. There was a lot of new information introduced in this short 3-day section, but your students will have plenty of opportunities to review these ideas through the review and preview sections in future lessons, and also in class when they complete the upcoming and long-awaited robot battle problem in section 11.4.